All right, good afternoon. If I can get you to do me a favor and open up your books, please, to the problem set on, well, there was some stuff on page 204, but I had told you, I really didn't care if you did those. That was about finding X and Y intercepts, and as elementary as that is, that's something that we're going to have to do whenever we graph functions in this chapter. It's just that we're going to have to, on top of that, do a first derivative and a second derivative and all kinds of other things. So I don't know if you have any questions dealing with the intercepts. I was more interested in the concept of symmetry and functions having odd symmetry, even symmetry, or neither. So can you take a look at that work, particularly on page 206, and see if you have any questions you would like me to go over. All right, seeing none, we're going to move on here and look at vertical asymptotes today. So this is section 5.1 of your textbook, lesson 5.1. What happens here when we get into a calculus course and we start talking about asymptotes, both vertical asymptotes and horizontal asymptotes, is that we come up with a more sophisticated explanation for what's going on. In Math 30-1, at the end of Math 30-1, when you learn about graphs of rational functions, you simply say that, and if you're in Math 30-1 right now, this won't really make too much sense to you, but in Math 30-1, we just say that there's a vertical asymptote if you have a non-permissible value of x that's not a whole. In other words, if you have a factor in the denominator of a rational function that has a 0, there's going to be a vertical asymptote there. And that's still going to be the case. And I'll formally discuss that with you in this lesson. But there's something else important here that we don't really talk about too much in Math 30-1, and we certainly don't analyze in the way we're going to analyze it in this course. So what a vertical asymptote is it occurs at some value of x, I'm just saying x is equal to a, when there's a discontinuity of the function, and here's where the definition gets a little bit more convoluted, such that the function is approaching infinity or negative infinity as you get closer and closer to a. What does that mean? It means that there's a discontinuity, so the graph going from left to right has a break in it somehow, but as you get closer to that break, the graph takes off upwards to infinity and or downwards to negative infinity. And the reason for that, of course, is that there is a factor of x minus a in the denominator of the function somehow that's a non-permissible value. Okay, and it's not really important or germane to this discussion today, but there cannot be an x minus a in the numerator, because if there is, it's not an asymptote. Okay, but I want to talk about that infinity thing. For example, if we consider the most basic rational function f of x equals 1 over x, we know what this looks like. You learn what this looks like in Math 20-1. When you are taught about reciprocal functions and their behaviors, and then we go over it again in 30-1 when we talk about rational functions. We learn that what this graph looks like is that there is a vertical asymptote at 0. There is also a horizontal asymptote at y equals 0, but we can't today get into the reason why there's a horizontal asymptote there. We're going to deal with that on Monday. And if you were to use a table of values or a little bit of common sense, which essentially is, I'm getting at, if you were to construct a table of values in your head, if we take a number like 10 for x, and you put x equals 10 into that function, you're going to get a y coordinate that's small, 1 over 10, 0.1. On the other hand, so you're going to get a point over here someplace. On the other hand, if you take a point with an x value, say, of 0.1, then the y coordinate would be 1 divided by 0.1, which would be 10. This is the nature of a reciprocal function or a reciprocal operation, is that if this is at 10, 0.1, there is going to be another point over here, and the coordinates of this point will be at 0.1, 10. We could also figure out that when you get over to 1, you will have a point, that's better. You will have a point at 1, 1. You know what, I'm not even going to put that point in there. It's not important. So this is not going to be perfectly to scale. The bottom line is this is going to be a curve that is asymptotic against both of these asymptotes. So it's going to be asymptotic against both, and what that means is the graph will always get closer and closer to those two dotted lines. This is where we would stop the explanation in Math 20 or Math 30, and we would just say, well, that's the meaning of an asymptote. The graph, as you go further and further and further away from the origin in either direction, the graph will get closer and closer and closer to that asymptote, but it will never reach that asymptote. And by the way, you're going to get an identical piece. All right, sorry about that. So it turns out that 1 over x happens to be called a hyperbola, and it has two branches to it or pieces to it. And the exact nature of this graph is not what's important. What's important is the description here that I said for a vertical asymptote. That there's a vertical asymptote at a particular value of x if, as you approach that value of x, y approaches infinity. And what that means over here, since we have a vertical asymptote, at x equals 0, it means that the limit as x approaches 0 from the right of the function, and the limit as x approaches 0 from the left of the function will be giving us infinite values. So when you look visually at the graph and we're approaching from the right the value of x equals 0, that means we're at x equals 8 and 7 and 6 and 5 and 4. It's all the way down. We're getting closer and closer to 0. But no matter how close we get, the function takes off to infinity. So what we end up having here is something that prior to today, you would have looked at this graph and you would have said the limit doesn't exist, because the function doesn't even exist there. So you would say correctly, I might add, that the function doesn't approach some value, but it approaches some concept. And the concept is it approaches positive infinity. And when you approach x equals 0 from the left, and I'm not really sure why I put a 1 on that negative. We wouldn't normally do that. But when we approach x equals 0 from the left, you can see that the graph takes off to negative infinity, so we would say that the limit is negative infinity in value. Again, I don't think there's anything wrong with you saying the limit from the left and the limit from the right don't exist as numbers, but they exist as ideas. So this is what we mean by saying we have a vertical asymptote. As you approach x, y approaches either infinity or negative infinity. And by the way, vertical asymptotes don't have to be oppositely asymptotic on both sides. Meaning, just because we approach infinity on one side of the asymptote doesn't mean we have to approach negative infinity on the other. We can have asymptotes that are both positive in terms of growth on both sides, so they both go up to infinity, or they can both go down to negative infinity, or one of each, or maybe the function doesn't even exist on one side, and we will see cases of that. So we're basically doing one example today dealing with this. It says, first of all, part A, we have an equation of a function x cubed over x to the 4 minus x. Determine the equation of all vertical asymptotes and use limits to describe the function on both sides. So the first thing you need to do with any functions analysis is factor everything completely. It's no different everybody, than analyzing a derivative. If you're going to analyze a derivative, you have to have the derivative in factored form. If you're going to analyze a second derivative, which we haven't done yet, analyze the second derivative we haven't done. If you're going to analyze a second derivative, you need it in factored form. So all I've done so far is I've factored an x out of the denominator, and now I can factor this further. I can write it as x cubed over x, and then the x cubed minus 1 factors into x minus 1, x squared plus x plus 1. We are actually in the same arena as we were when, I think, Arden had asked a few days ago, do we have to factor that difference or sum of cubes to proceed? Not really. Because what we can see by looking at this is that we are going to have, because of this, a vertical asymptote at x equals 1. So I just want to start with that. And a lot of what I'm doing here, in fact, everything I'm doing here so far with this example is what you would do in Math 30. It's got nothing really to do with calculus just yet. When you take a look at this factor, this has no zeros, so there's no vertical asymptote. In fact, I would go a little bit further there and say, for that quadratic, which is never factorable and never zeroable, we've mentioned that a few times, that trinomial factor out of a sum or difference of cubes is never factorable or zeroable. What that means is there's no non-permissible values associated with that trinomial. Now, there is a non-permissible value associated with this x. X cannot equal to 0, but, and this is where, if you're in Math 30-1 right now, you're missing out on just a little bit. Because that x in the denominator cancels with an x that's identical, a factor that's identical, x, in the numerator, there's a hole at, I guess, you know, I said x is the 0 of the bottom is 0, but maybe we should be explicit and say what that means is x cannot be 0. It's a non-permissible value. We will have a hole at x equals 0. Okay. And now I kind of struggle with this in teaching calculus in saying, dude, does it really matter if we cancel one of those x's? I mean, we could cancel it. I could write, instead of having that function that I have in factored form, I could write y equals x squared over x minus 1 times x squared plus x plus 1. Where I struggle with this is if I write this, this is not the function. Why not? Like, what would I have to include here? Evan, do you remember? Right, I would have to say that x is not allowed to be 0 because by canceling that x over here, 1x out of the x cubed with the x on the bottom, I maybe give a student the misconception or the wrong idea that means that all of a sudden we are allowed to use x equals 0. We're still not allowed to use it. And by the way, we don't have to, but if you did rewrite the function, you could probably as well put and not equal to 1, although I say you don't have to because it's right there still. For this reason, I think it's better for us to just leave the function in this form. Okay? So all we have is a vertical asymptote. What were we asked to do here? Determine the equation of all vertical asymptotes and use limits to describe the function on both sides of the asymptote. All we have is an asymptote at 1. So that means we have to determine the limit as x approaches 1 from the left of the function. And here, it doesn't really matter what you write. I'm just going to write f of x. And we also have to determine the limit as x approaches 1 from the right of the function. And all this means, everybody, is this is a reminder because it's been so long since we've done left and right-handed limits. There's no real algebraic way to do this. There is, but I'd rather not touch on it right now. What you need to do is take a number that's very close to 1, but to the left of 1, and put it into the function and see what you get. Now, before you start, here's the important fact. We know that at 1 there's an asymptote, which means one of these limits have to be equal to infinity or negative infinity. So all we have to do is decide whether we get a positive output or a negative output. And I will tell you right now, this is getting a little bit messy to think about and talk about, but the closer to 1 you get, the value of x that you put in, if it's closer and closer and closer to 1, if you get a positive number, as you get closer, you'll just get a larger positive number because it's going to explode towards infinity. So I'm going to write the function here just so I can refer to it in my explanation. We have, and you know what, it doesn't matter which one we put. I am going to put this one and explain to you that there is, this I guess maybe is an algebraic way of doing it. So I am not going to, I'm going to ask you to follow along very carefully here. This is thought-provoking. This isn't simple. I am just going to pick a number that's a little bit to the left of 1 and ask myself what this thing would look like. If I put in a number like, this is what I'm thinking, (0.9). That's close to 1 from the left. Let's not quibble about how close it is. I will get a positive top because I'm going to square it. I will get on the bottom that x minus 1 will be negative because I'm taking that number that's a little bit less than 1 and I'm subtracting 1, so it's going to be negative. I will get for this other factor a positive because all three of these terms are going to be positive. So I can see looking at this, everybody, that I am going to get an output that's negative. What does that mean? It means that without actually calculating y, I know that this limit will be negative infinity. Now, if that doesn't do it for you, then I suppose what you could do, oh, interesting. Then I suppose what you could do is take that function, I'm going to put in the original function here, which was x cubed, divided by, in brackets, x raised to the 4 minus x. I want to make sure that's right. Was that what it was? X cubed over x to the 4 minus x? And I don't want to look at the graph. I don't want you to see the graph yet, okay? Even though you might have just seen it. And I'm going to set up my table to be on ask, and I'm going to go in here and demonstrate to you the asymptotic nature to the left of x equals 1. I put in 0.9, and I get negative 3 almost. I put in 0.99, which is even closer to 1 from the left, and I get negative 33. I put in 0.9999 just for kicks 456, which is really close to 1 from the left, and I'm getting negative 6,127. The point is, as I get closer to 1 from the left, y explodes in a negative direction. We can do the same kind of thing from the right. So now what I'm doing from the right is I'm imagining putting in a number like x equals 1.1. And I think many of you can see that you're going to get a positive out of this. But just to drive that home, if I put in 1.1 for x, the top of this expression, what I'm pointing at right here, is going to be 1.1 squared. And I don't care what number that is, I care that it's positive. Because I already know it's an asymptote. I have to get plus or minus infinity. On the bottom, when I put 1.1 into this factor, I'm going to get a positive. By the way, you don't need to know this, but some of you may appreciate it's this factor which is making the whole thing really big. Because when you put in a number close to 1, that factor will be very tiny, making the whole fraction big. And as we said, this is positive everywhere, which means that this will be positive infinity. And you could have done both of those by entering the function in your calculator somehow and then putting in numbers that are very close to 1 from the left or the right. Does anybody have any questions about finding those two limits? Okay, before we turn the page, all that is important here is you understand that, and I do want you to just sketch this grid that I have here, and you can put in the vertical asymptote. Just do a quick little sketch there of it. All that is important is that this tells us the graph looks like that close to the asymptote. When we said that as you approach 1 from the left, the function approaches negative infinity, that's what that means. Let me highlight this for you. This statement is telling us about this part of the graph. Because we're to the left of the asymptote, the graph is pointing towards the floor, towards infinity. On the other hand, this statement is telling us about the behavior of the graph there. That's all the limits tell us. Okay? So let's turn the page now and let's take a look at part B, which is asking you to find the X and Y intercepts. So if you are asked to find the y-intercept, this is where you let x equal 0, right? Is this on the same page? Okay, so not turning the page. If you're asked to find the y-intercept, this is where x equals 0, but x can't equal 0. It's a non-permissible value. So think about what that says. If x is never equal to 0, and x equals 0 is on the y-axis, that means there will never be a y-intercept. This graph has no y-intercepts. So this is not permissible. Which means there's no y-intercept. If we want to find x-intercepts, then we let y equal 0. Well, I want to demonstrate something to you. If I let y equal 0, then this becomes 0 equals x cubed over x to the 4 minus x. We have to solve that equation for x. And I know that you could cross multiply, but I think that's a mistake. What you want to say here is that the only way a fraction can be equal to 0 is if the top of the fraction is equal to 0. If I have a fraction a over b, and I say it's equal to 0, then the fact of the matter is a has to be 0. You cannot get 0 for a fraction unless the numerator is 0. So what that means is that in solving this equation, you're really solving this equation. And keep in mind, I have not cross-multiplied to get rid of the denominator. That's a flaw logically in thinking. You should never get rid of variables by manipulation. And I solve this and I go, oh, the x-intercept is 0, except that's not possible. Which means there's no x-intercept. This graph will never make contact with either axis. And now we're going to put this all together and graph it and talk about, well, we have to talk about the horizontal asymptote a little bit here. So part C, this is on the next page, I believe. Part C says, perform a first derivative test to determine any max-mins. Okay. So our function was y is equal to x cubed over x to the 4 minus x, but that turned into y is equal to x squared over x cubed minus 1. Do you remember that bit of business that we factored an x out of the bottom? Now, yes, it's true, x is still not allowed to be 0, but, and I don't think this has come up, even though this is technically not the function because it doesn't include the non-permissible value, the derivative of it will still be the derivative of the function. In other words, you can simplify the function first before you differentiate. So we're going to differentiate that. The other thing you will notice is that I didn't leave the x cubed minus 1 in factored form because I'm about to use the quotient rule. Why would you have a product in the denominator for the quotient rule? I think that would make things problematic. So I'm looking at this one that I've got wrapped in the green ink. dy dx is the derivative of the top, which is 2x, times the bottom, which is x cubed minus 1, minus the top, which is 2x, pardon me, minus the top, which is x squared, times the derivative of the bottom, which is 3x squared, over the bottom squared, which is x cubed minus 1, quantity squared. Take a minute and just walk through step by step all of the pieces of that and make sure that you are okay with that derivative. Okay, so we factor. I'll be honest with you, and the thing I like about this lesson is you're not really learning too much new, but there's an opportunity for me to give you more and more tips about the algebra. Technically, we should be factoring an x out, but since multiplying it out would only lead us to 4 terms, it'd be just as easy to multiply it out. And that's what I'm going to do here. If I multiply this out, I get 2x times x cubed, which is 2x to the 4. I get 2x times negative 1, which is minus 2x. And then I have x squared times 3x squared, which is minus 3x to the 4. So I get 2x to the 4 minus 2x minus 3x to the 4. And then this is over the denominator of x cubed minus 1 squared. Had you factored an x out of both terms in the numerator first, then you would have less to factor now. Okay, but because there's only 3 terms, it's very simple. So your next step would be to bring a little bit of stuff together on the top. I have negative 2x, and then I have minus x to the 4. Pardon me. Yeah, that's right. So I have 2x to the 4 minus 3x to the 4, which is negative 1x to the 4. And then I also have a negative 2x, and this is over x cubed minus 1, quantity squared. Not quite done here. We should factor this. I will explain why the factoring of it is really important here in a second, although I hope many of you know why it's important. So I have dy dx equals, I'm going to take the negative x out. Man, I don't like all those negatives. You can leave them in, it's not going to matter. But if I do take the negative x out, then I have 2 plus x cubed. And this is over x cubed minus 1 squared. The reason I factor this, there's a couple of reasons. The reason I factor it, first of all, is because I want to be able to see what the critical values of x are. And I can see there is a critical value of x at 0 because of this factor. I can see there is a critical value of x of 1 because of this factor. And I asked my math 30s this morning, and I'll ask you, the highlighting does help, doesn't it? It's not confusing when I do that? Okay. I just wanted to make sure. Because I've been doing it for a long time, and I never really have asked. And then we also have a critical value of x, and I will show you how I'm getting this in just a second, but I think most of you will see how I'm getting it, of the cube root of negative 2. And that critical value of x comes about because of this factor. And by a show of hands or thumbs up, how many of you would be able to look at 2 plus x cubed and say, oh, it's the cube root of negative 2? Okay, if you can't, then what you're going to have to be doing is saying, what is the solution to this equation? You have to solve that equation, which means you have to subtract 2 from both sides, and then you're left with x cubed equals negative 2. And then you take the cube root, and anyway, that leads you to here. It's always useful, because this is the other reason we're factoring things, because we have to do a first derivative chart. It's always useful to identify a decimal value of an irrational number so you know what we're talking about. So what is the cube root of negative 2? Approximately. Well, we can do that on our calculator, obviously. I do cube roots by raising things. I do cube roots by raising them to a third. You can feel free to use the cube root function. I just don't like poking around in the math menu. It's about negative 1.3 approximate. So we need to set up a first derivative chart that goes from negative infinity to the cube root of negative 2, from the cube root of negative 2 to 0, from 0 to 1, and from 1 to infinity. So negative infinity to the cube root of negative 2. I don't know that it really matters, but many of you will recognize we could write the cube root of negative 2 as negative cube root of positive 2, if you wanted to. Then we have to go from the cube root of negative 2 to 0, from 0 to 1, from 1 to infinity. Just an internal check here. If there are 3 critical values and we're breaking up the domain of all real numbers with 3 cuts, we should get 4 intervals, and we have them. Across the top, we're going to put all of the factors of the derivative. One of the factors was negative x. One of the factors was 2 plus x cubed. One of the factors was x cubed minus 1, but it was squared. Am I correct in getting all of the pieces of the derivative there? I am. Okay. So negative x will be positive, and then switch to negative. as it passes the 0 of negative x. I hope everybody remembers that normally it's negative to positive. Why did it flip? Because x is negative in the factor. The negative to positive thing, by the way, everybody, and I'm not just hand waving this away and writing it in and then not talking about it. The negative to positive rule works with any odd degree factor. So x cubed is an odd degree. If it's positive x cubed, it will go from negative to positive. If you're unsure, you can go ahead and put in a number in this interval and put that value of x in here and convince yourself you get a negative, and then you could proceed in that fashion. But you don't have to. And lastly, the last column here will be positive throughout, because it's x cubed minus 1 squared. It's squared. It doesn't matter what x cubed minus 1 is, you're going to square it and get a positive. This tells us that the derivative will be negative, then positive, then negative, and then it's still negative. That tells us the function in this interval is decreasing, it's increasing, it's decreasing, and it's continuing to decrease. So that tells us that we have a minimum here, because the function goes from decreasing to increasing. This is what I've referred to many times in this course, that we've already done this. We've talked about this in at least 2 or 3 other lessons. Do we have a maximum here? Is there a maximum there? Why not, Arden? Right, it's a non-permissible value. So the function doesn't exist there. There's nothing there, graphically. We have nothing occurring here as well. We have nothing occurring here as well. But even if the function did go from decreasing to increasing, it wouldn't be a minimum, because this is also non-permissible. Now, we have to use this idea. What else do we have to do here? Along with everything else we've collected, with the added information that the x-axis is a horizontal asymptote, because you don't know how to find it yet. I mean, you kind of do. I've taught you a little trick in Math 30-1, but you haven't learned the calculus way to find a horizontal asymptote. So what we know about this function is that we have a vertical asymptote at 1. You're told you have a horizontal asymptote on the x-axis, and you're told that because you don't know how to find that yet, which we're going to learn officially on Monday. What else do we know? We know there's a minimum, rather, don't we? Yeah, there's a minimum at the cube root of -2. So we got to do just a little bit of work here. We have a minimum at the cube root of -2. We need to have the y coordinate of that point so that we can determine where it is on the graph. And there's nothing wrong with you using the simplified form of the function. But again, I need just a little bit of help here. Is that the simplified form of the function? Disregarding the non-permissible values. That's what we got. So we're going to put that in. And I really don't see the need in finding an exact value here. I mean, I could write the cube root of -2 quantity squared. Actually, you know what? Maybe we will. I'm going to go back on my word here. I'm going to put that in. We will have the cube root of -2 quantity squared over the cube root of -2 cubed. I don't know why I put brackets there, -1. I am going to do this. Because we get, well, why not? we get negative 2 to the 2/3 over negative 2 minus 1. I'm combining my root of the third root with a power or exponent of 2 to get an exponent of 2/3. When I cube the cube root, those two cancel, so on the bottom that first part becomes negative 2 minus 1. So then I end up with the following. I end up with negative 3, and I'm going to put the negative for the 3 on the top. And I end up with 2 to the 2/3. And some of you might go, where's the negative on the 2? Since I'm squaring it, it becomes positive. Okay, you don't have to do that. You could leave the negative with the 2 and have a negative and then times negative 2 to the 2/3. But this is what y is equal to, so approximately come on, you guys, let me know. My calculator's not on. Let me do that again. Negative 2 raised to the 2/3. And by the way, just so you know, that doesn't mean I'm taking negative 2 raising to it. It's negative of 2 raised to that. And then I need to divide by 3. So did anybody actually calculate this directly and get about negative 0.529? Hopefully. That's the value. So it's about negative 0.53. So now we have to put this all together. Let's see. I've got my asymptotes in there. I know, and I'm going to draw something here, but I don't want you to commit to it on paper. I know that whatever we draw, it has to go down here and up there. We've already determined that from the limits on the left and the right of 1. I've also just determined that there is a minimum at negative cube root 2, which was about 1.26. Is my memory right there? That when you take the cube root of negative 2, you get about negative 1.26, comma, negative 0.53. So we can put that point on here. Negative 1.3, comma, negative 1/2. Keep in mind, if this is 1, this is 2, this is, I'll maybe move this a little bit, this is negative 1. Yeah, I had it in about the right spot. This would be about negative 1.3, comma, negative 1/2. Okay. Keep in mind, again, those two green arcs are just guidelines. I haven't done anything. I'm not committing myself to that yet. Now, here is a tip that you're going to have to get used to doing. Across the top of your graph, you can put a line. It doesn't have to be perfectly straight, but we're going to put a line there, and we're going to mark off on the line our critical values for the derivative. So we had x equals 0 being a critical value. These are critical values for the derivative. We had a critical value at the cube root of negative 2. We had a critical value at 1. Which means, everybody, if you look at the top here, left to right, there are 4 sections to this graph that the first derivative tells us about. The first section of the first derivative tells us the function is decreasing. Okay? But we know there's a horizontal asymptote on the x-axis. So how can the graph be decreasing as we get closer and closer to that green dot? Well, the only way it can be decreasing to that point is if it's asymptotic here. Right? Because the x-axis is a horizontal asymptote. So it's going to be decreasing to that point. Now I'm going to ask you to add something more to that top line. Take a look at your first derivative chart and see if this makes sense to you. That the function left to right is decreasing, and then it's increasing, and then it's decreasing, and then it continues to decrease. So do those match up with our 4 intervals in our first derivative chart? What we're doing here is I'm taking this information, I'm taking that, and I'm showing it to myself for x, because that's what that chart is showing. Those are x intervals. And that means when I draw left to right, I have to draw down, and this has to be a minimum, and then it goes back up. Now, was there, this is the goofy thing about this graph, at this point here, where the graph goes from increasing to decreasing, was there a maximum? No, because it's a non-permissible value. And now I have to go back to Math 30, and some of you are going to be at a disadvantage here. Our function was y equals x cubed over x times x cubed minus 1, correct? There are a lot of different ways we could write this function, but I'm just writing it with the bottom factored but nothing canceled. Who can tell me what is happening at x equals 0? And this is from Math 30. Evan again. There's a hole. So there's a hole. This is the rule from Math 30. If you have a factor in the denominator that produces a non-permissible value, in this case x can't be 0, but that factor cancels with an identical factor in the top, then that x equals 0 is not an asymptote. It's not a vertical asymptote, but it's a hole. So we have a hole at 0. In fact, you know what? I think I've already mentioned that, right? But how do we find the y coordinate of the hole? Does anybody remember that? Yeah, Makai. Right. Put it into the function, and this is going to seem weird, but it works. You see this thing right here? Hope that wasn't a mistake. No. Right there, see it says x is not equal to 0? Too bad. We're going to put x equals 0 in anyway to find the y coordinate that's not allowed to be there. And if you put in the x coordinate of 0, if you put 0 in for x in that, you're going to get 0 over negative 1, which is 0, which means there's, I think, Liam, you might have said, there's a hole at the origin. Was that you? It was Evan. We've got not just a hole at x equals 0, very specifically, we have a hole at the origin. So there's a hole at 0, 0. We can put that in. And now we can complete the graph, because from this minimum point, and I'm not really happy with my caffeine-infused shakiness here, but it goes down, there's a minimum, and then it goes up, and then it has to change direction and go down, but be asymptotic. So when you look at those arrows at the top, that's guiding me for what I'm drawing, whether I draw towards the sky or towards the floor. And then if it is asymptotic on the right side of that x equals 1 asymptote, and it's also asymptotic on the x-axis, if you look up here, the other part of the graph could look like this, or it could look like that. But we know it has to look like the top piece, because it has to be decreasing from left to right. And these things are going to get more complicated. They end up being almost puzzle-like, that you get all this information and somehow you have to get the graph together. And sometimes you have to say to yourself, I'm just going to resist the urge to look at my graphing calculator. Don't look. Try it. if you ever find yourself, and it's going to get more complicated, but if you ever find yourself backed into a corner where you feel that it's impossible to draw the graph so that it meets all of these conditions, then you've probably done something wrong. Like if I get, my derivative had a negative in front, right? If I forgot about that negative, everything would be backwards and nothing would work. We can take a look at what this graph looks like. I know I asked you to put this into your graphing calculator for y1 so that we could look at the table. I think we were doing that for the left and right hand limits. Yeah. But now we can set up our window settings to kind of match what I have here. If this is -1/2, then this is -1. I'm going from about -2 to 2 vertically. And horizontally, it looks like I'm going from about -3 to 2. So in my window settings, my minimum x is -2, my maximum x is +2. For my y's, I'm going from -2 to +2. Looks okay. That's pretty good. And the beautiful is maybe the wrong word. I think it's a beautiful idea. The beautiful thing here is all of this calculus and all of these rules are allowing you to graph a function, and it could be any function. In other words, everybody, you don't say, oh, it's a quadratic function, I have to complete the square to find the vertex. Oh, it's polynomial, I need to find the zeros and use all of the rules about even and odd functions. You just say it's a function. What do? I find the derivative, I find the intercepts, I find the asymptotes. Any questions with that example? Yeah.
Really, we don't have to worry about finding the limits as long as we find the, or do our...
Yeah. Evan's making the point here that when we found the left-hand limit to be positive infinity and the right-hand limit to be negative infinity, that's kind of just backup information. Because if you draw it without that information, but you're looking at this as guiding your every move, then that subsumes or that includes or that takes into account the left and the right-hand limit. And you're going to find, we would call that a redundancy. We've found that information in two ways. You'll find there will be other redundancies that once we do the second derivative and we put it all together, sometimes you go, oh, I guess I didn't really need the first derivative for this part of the graph because the second derivative reveals it. Any other questions? I was a little lazy here in drawing this piece in the top right corner. It's probably curvier rather than more angular. All right, then you can see on page 212. I don't know what I was working on something with another student. On page 212, questions 1 to 4. Get to work. And Zach and Demi, I have a question for you. I don't know if you can type out an answer. I'm just curious. On your candy box assignment, you both used the second derivative test. Has somebody there shown you that? So somebody's teaching you that, okay. The only thing I would add is in the future, if you're going to use the second derivative test to confirm which critical value of x is right, write in, and Demi, I think you did on yours, you wrote, oh, a maximum has to have a second derivative that's negative, and then that's fine. But if you just find the second derivative at each of the 2 points, and one is positive and one is negative, and you cross off the one that's wrong, you just should in the future explain that, oh, I'm crossing it off because a maximum has a negative second derivative, not a positive second derivative. Anyway, I wanted to make sure that somebody has taught you that. And does the second derivative test make sense to you? That if it will make more sense when we learn about something called concavity. Anyway, thanks for letting me know. And I have those assignments marked. I'll hand them back to you guys here on site today, and I will email them to you, Demi and Zach. And I'm just checking. Nicole's not there today, right? Okay. And I'll email them to you a little bit later this afternoon.